Hello. So in this video, we're going to continue our proofs of limit theorems of functions. And in particular, we're going to show that if you have convergent functions f and g with limits L and M, then the limit of the sum is the sum of the limits. The limit of the difference is the limit of the differences, or the difference of limits. And these basic properties on just the operations of addition, subtraction, multiplication, and division, where division again is going to only be defined when you have a non-negative denominator or non-zero denominator. Now, the theorem that we're going to prove today is similar to what we have proven before with sequences. Now, if you've seen those videos, or if you remember how we proved these limit theorems for sequences, it took us quite a while to get through those topics. It took us, I think I have 4 or 5 videos on just proving these limit theorems for sequences. And now we're at very similar limit theorems for functions, except for now it's not going to take as long to prove them because we've built up enough theory to where the statements that we're going to prove are just more or less consequences of what we've done before. And that's why I have these 2 theorems up here already written, namely the sequential criterion theorem of limits, and then more or less a version of like a squeeze theorem type of thing with constants from chapter 3. So let's just like recall what these things say. So the sequential criterion of limits for functions says that we have an equivalence between the definition of the limit of a function and a statement about sequences. And what does it say? It says basically that if C is a cluster point of A, and then the limit of f as x approaches C is equal to L is equivalent to saying that for every sequence xn and A that doesn't equal C and converges to C, for every one of those sequences, the limit of the sequence f of xn is equal to L. So this, if and only if this for any sequence xn contained in A, where xn never equals C. So this is a very useful theorem. We spent an entire video on the proof of that, and we'll see how useful it is in a moment. The next theorem states that if we have a convergent sequence that is bounded below and above by constants for every natural number n, and if that sequence converges, then the limit is also bounded above and below by those constants a and b. Okay, so let's go ahead and look at how maybe with addition of 2 convergent functions, we can apply the sequential criterion to get a really short proof. So I think in the textbook, maybe this is a part of a theorem. So 4.2.4 theorem. Okay, so I'm going to say let A be some subset of the real numbers. And then F and G are going to map A to R. Okay, so this is just 2 functions defined on A. And let C be a cluster point of A. Okay, so then if the limit as x approaches C of f is equal to L, and the limit as x approaches C of G is equal to M, then the limit of the sum of the function, so as x approaches C of f plus g of x is equal to L plus M. So this is just a part of that theorem. The theorem has all the standard operations, addition, subtraction, multiplication by a constant, multiplication between the two functions, and quotients of these functions. But because I have limited board space, I need to break it up. All right. So this is a standard standard technique that you take for granted in Calculus 1. When you're learning about limits, you apply the limit of the sum is equal to the sum of the limits all the time. So now we need to argue why it's true. So this is real analysis. We have to enforce some rigor into the mathematics that we know. So now there's two ways to prove this. You can prove this using the epsilon delta definition, which is going to be a homework assignment. I'm going to prove it the other way using the sequential criteria. Okay, so suppose this and that. So suppose the limit as x approaches c is equal to L, and the limit as x approaches c of g is equal to m. And let x sub n be a sequence in A. With x sub n not equal to c for all natural numbers n, and the limit as x of x of n equal to c. Okay. Now, this sequence satisfies this property here, right? Which means that this holds for that sequence. The limit of f of that sequence is going to be equal to L for f and equal to m for g. So then by theorem 4.1.8, we have the limit of f of xn is equal to L, and the limit of g of xn is equal to m. And this holds if and only if that part holds. And it's an equivalence between these two statements, which is always nice. So limit of g, that looks kind of funny, but all right. So then, right, by the way that this function is defined, right, just recall that, so maybe recall that f plus g of x is equal to f of x plus g of x, right? So then, let's apply that together with this. And the limit of f plus g of xn, right? This is equal to the limit of f of xn plus the limit of g of xn. And the limit of the sum is the sum of the limits. Well, in this case, it is, right? Because this is defined as that sum. But this, we know that that converges and that converges. So thus, this limit equals that if and only if this holds, right? Thus, again, theorem 4.1.8. Establishes maybe that the limit as x approaches c of f plus g of x is equal to L plus m. Okay. Now this same argument, like this also shows that the difference is going to converge as well, right? Like if this were like a minus right there and there's a minus right there, then all of this stays the same. And then instead of a plus, you have a minus, 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 minus. So this same argument shows that f minus g converges to L minus m. Okay. And also, the same argument shows that f times g, right? So f minus g of x is equal to f of x minus g of x, and then f times g of x is equal to f of x times g of x, right? So then the same exact argument will show that the limit of this is equal to the limit of that, and that is equal to the limit of those, and that is equal to the limit of those. And in a similar fashion, you can show f of g of x. So using this definition, provided g of x is not equal to 0 for all x in A, you can do the exact same argument to get that the limit of the quotient is the quotient of the limits. And just like that, we've established that all the fundamental operations on these functions, we have all limit theorems by this one argument using the sequential criterion. Okay, so I leave that to you to write on your own because it really is the exact same, just being careful that you don't divide by 0 in this case here. Okay, so let's prove our next result. I'm going to go ahead and pause the video so I can wipe down the board, and then we'll prove our next result. Okay, so let's go ahead and finish up this video with a quick proof and a statement of quick proof of this theorem and a statement of one word theorem. So what does this statement say? Well, if we have a function f and a cluster point C, then if f is bounded by constants a and b for all x in its domain with x not equal to the cluster point C, and if the function converges as x approaches C, then the limit of the function is also bounded above and below by b and a. And now this is very similar to this theorem here that we proved a while back on sequences. So in fact, because we have these tools already proven, this is really a very short proof. So let's go ahead and work this out. So we're going to go ahead and say suppose a less than or equal to f of x less than or equal to b for all x in A with x not equal to C. And that the limit as x approaches C of f is equal to L. Okay. So we're supposing that it converges and it satisfies this property. C is just some cluster point of A. Okay, so then we're going to use the sequential criterion, and then we're going to apply this theorem here. So next, let Xn be a sequence in A with Xn not equal to C for all naturals n. And the limit of x sub n equals C. Okay, so by the sequential criterion, or theorem 4.1.8, we know something about the convergence of f evaluated at the sequence. So then by theorem 4.1.8, the limit of f of that sequence is equal to L. Okay. So we know that we have a convergent sequence. It's bounded and satisfies this, right? So we can just finish it off by saying that is the sequence of the images of Xn under F is a convergent sequence where the terms are bounded by A and B for all naturals n. So then we just apply this theorem and we're done. That's it. So then by theorem 3.2.6, A is at most the limit oh no, I can say that. That which is equal to limit as x approaches C of F, which is at most B. And then we're done. That proves the theorem. Okay. So under this hypothesis here, okay, we have this result, but we also have another result, 4.2.7, which is a direct application of, well, not this, but a direct application of this over again. And that is that, I'll go ahead and write out the whole thing. So let A be a subset of R, F, G, and H map A to R, and let C be a cluster point of A. Okay, so then if f of x less than or equal to g of x, which is less than or equal to h of x, for all x in A with x not equal to C, and if the limit as x approaches C of f is equal to L, which is equal to the limit as x approaches C of H, then the limit as x approaches C of G is also equal to L. And it really is a direct consequence of what we just proven. So I'm not even going to write out the proof. I'll leave that as a homework exercise. This theorem, I already guessed. This is the squeeze theorem for functions. Okay. Okay, so with that, that's all the basic limit theorems of functions. It only took 2 short videos to get through all of these theorems, but that's it. So now we can move on to in the coming videos, continuous functions, the most important functions that you'll encounter in real analysis. Before I go, though, I'd like to say that this is going to be homework for this section. So 4.2 homework, and this will be due next week. I'll post it on Blackboard as well. 1, 2, 4, 6, 7, and 11. So what is today's date? Let's see. May 4th. Okay. Okay. That'll be it. Thank you for watching.